Good morning, everyone. I'm Karthik Pattaje. I'm presenting some of the work that I did during my PhD under David Lang's guidance at the University of Illinois. I'm currently an associate engineer with Jenny Elsner. The title of my topic today is using vibration to control the rheology of concrete for 3D printing. So obviously, it's a new technology. We don't already have a mixture design procedure for 3D printing. But I was thinking about if we were to have a mixture design procedure for 3D printing, how would we go about it, right? The guidelines are by 211 and it's for normal density concrete. So eventually down the line, we should have something for 3D printing in here, right? 3D printed concrete is also normal density concrete. One of the first steps in the procedure is to figure out what the slump should be. That got me thinking, what would the slump for 3D printing, what would we call it? Do we want a low slump concrete or a high slump concrete? Because for 3D printing, we need both of these features, right? We need low yield stress or high slump concrete to get it to flow through the printer, and till it extrudes, we want a fluid-like behavior. But once it does extrude, we want it to have a solid-like behavior so it can hold its own shape as well as take the load of subsequently placed layers. So, how do people do this? Usually cement paste or cement mortar is printed. The aggregate size is pretty limited, and there is a very high binder content in the 3D printed mixtures. Mohan et al. In their paper found that on an average, the binder content is about 800 kg per meter cube. That's almost twice our conventional concrete. So 3D printed mixtures, as it stands today, are very binder heavy, right? So it's not very sustainable, it's going to be expensive, and thinking long term, if 3D printing has to be really sustainable, the service life of structures printed with 3D printing have to exist a long time. But if we have such high binder content in our mixes, we will have issues with shrinkage, creep, freeze-thaw. These are issues that will come if we continue to print with high binder content. So actually having coarse aggregates will benefit us in all of these issues. But that would also mean we are printing traditional typical concrete for which we know the behavior already, right? Say workability, the title of this session, I guess. Predicting workability is pretty well known when it is conventional concrete. So can we do something similar? Print concrete, which we have been using for a long time. We have experience with this material. So that is where my work is focused on, actually incorporating coarse aggregate into concrete. Now, concrete thankfully has a dual rheological behavior. It can be a solid and a fluid simultaneously. And this is something we have been doing for a long time. We vibrate concrete. When you vibrate concrete, it can flow. You stop vibration, it stops moving. The yield stress is eliminated or seemingly eliminated at low shear rates, and response of concrete to vibration is instantaneous and reversible. This is a known feature of granular fluid. Hannerton et al. In 2015 came up with the rheological model for granular suspensions, not for concrete, any granular suspension, where they found out that materials which make up part of the system can carry a lot of the load in granular suspensions. In concrete, the aggregates carry a lot of the load acting on concrete, and it's suspended in a cement paste matrix. Now, these aggregates form a contact network, giving rise to yield stress. When you vibrate fresh concrete, the coarse aggregate to aggregate contact network is broken, and it loses a lot of its yield stress. So that was the basic idea for my work. But there is no reliable way to measure rheology of concrete when it is being vibrated. So what I did was modified an existing concrete rheometer by basically placing it on a vibration table and carrying out rheological measurements when the vibration table is vibrating. So the schematic. The basic idea when we were working on this is how it all started off, was to have very stiff concrete going in, and then use whatever method, get it to the nozzle. I say whatever method because you can have a pressure head, you can vibrate it to get it to reach the nozzle. Once the stiff concrete reaches the nozzle, you vibrate the nozzle. There's an instantaneous change in the yield stress of the concrete and it can flow out. Once it comes out, there's no more vibration and it should regain its no slump or low slump characteristics and be able to hold its own shape. This was the working idea. So this was my experimental protocol. At 8 minutes after water and cement came into contact, I did a flow curve test to measure the viscosity. It takes about a minute. Then on the same concrete, measured viscosity, but this time the vibration table was on, so measured viscosity with vibration on. Just before 15 minutes, vibrated the icariometer bucket to erase shear history, and then did a yield stress measurement. Now this is analogous to the first layer of concrete being placed. So this was the yield stress. Let's assume the nozzle takes 5 minutes to go around the print layer and come back to the same position. In these 5 minutes, concrete would have gained some strength, the green strength. The yield stress has increased. Let's say the nozzle after 5 minutes has come back to the same position and is vibrating. During vibration, the yield stress is reduced, so material is flowing out of the nozzle. And then the nozzle continues to move along the print path. The yield stress of the material that has just been placed, there is no more vibration, instantaneously recovers. And can do this multiple times to mimic multiple layers being placed. I did this for all of the mixes, but in subsequent slides, I'll only show the first 2 vibrations, or the results from the first 2 vibrations for different mixes. Now, a quick note on the nomenclature I'll be using. I used a volumetric mix design procedure. So, the names of my mixes, the first part is the actual water cement ratio I considered. Second part is volume of paste in volume percent. And then S0 is how much sand is in. So in this mix, it was completely paste. 0.4 water cement ratio, 70% of the volume is paste, 30% is sand, or 70% paste, S15, and the remaining 15% is coarse aggregate. I used 3/8 inch limestone chip as my coarse aggregate. Now all of my mixes, I sifted all the aggregates, separated them out into different sieve sizes and recombined them, so I had a good control of, it took ages. I see there's a space here. It took 2 years of my PhD basically to do that, and then recombine them all, so I had consistent control over what my aggregates were. Now, what is the effect of aggregate content on the rheology? So this is pure cement paste. You have, in my setup, I was getting about 200 Pascal when it was not being vibrated, about 100 Pascal when it was being vibrated. Next, the 3 lines that just showed up have paste of 85% and 3 different aggregate ranges. Either completely sand or completely limestone chip. It's a weird thing, but the other extreme, and somewhere in between, 50% sand, 50% chip. Next, I reduced paste further. The blue lines have 70% paste and 30% aggregates. Reduce paste further, reduce paste further, and reduce paste further. The red lines are almost an order of magnitude or more greater than just cement paste, right? When you have aggregates, your yield stress goes up significantly. But in all of these cases, when you're vibrating it, the yield stress goes down. So, and this is what we want for 3D printing. Once printed, you need high yield stress. When you are printing, you want low yield stress, right? So vibration can provide you this necessary duality of rheology. Now, in all my subsequent slides, whenever I say yield stress without vibration, I am basically talking about the 20th minute values, and yield stress during vibration is the average of the first vibration. The trends remain the same, so I'm only going to focus on those 2. The same data from the previous slide, I've plotted that again, but now the total aggregate volume on my x-axis and the yield stress on the y-axis. You'll see it's initially flat up to about 30% aggregates. This is because there is no aggregate to aggregate interlock, right? The paste rheology dominates initially. But when there is enough aggregates, they start coming into contact with each other, and you'll see an exponential increase in the yield stress. So as aggregate content increases, there's an exponential increase. So earlier I showed from 211 a slide saying how various parameters affect workability. So I'm going to build something similar, but this time for rheology. Okay. This slide will keep updating as I move on. So both yield stress and yield stress during vibration are impacted by the volume of aggregate in the mix. So what about water to cement ratio? I'm only showing 3 of the mixes here. Pure paste, 70% paste and 40% paste, and corresponding aggregate volumes at 0.4 water cement ratio. On the left, I have 0.36 water cement ratio. On the right, 0.44 water cement ratio. And you'll see water to cement ratio does impact the yield stress both when it was not being vibrated and when it is being vibrated. Right? Time to update the table again. So there is an inverse relationship between yield stress and the water to cement ratio. Next, the effect of sand to chip ratio. So keep a constant paste, but within the total aggregate volume, what if we change the packing, basically sand and coarse aggregate? There were 2 mixes right at the top, which were beyond the capability of the icariometer to measure. This was when the aggregate was completely sand or completely limestone chip. They were just too stiff. But during vibration, you will see that I was able to measure. It's really high, pushing the limits of the icariometer, but I was able to get something. Now, the solid line is my control, 50% sand, 50% coarse aggregates. The dotted line has more coarse aggregate than sand, and the dashed lines have more sand than coarse aggregate. You'll see there is a minima. When you have equal amounts of sand and chip, you have the lowest yield stress in a given condition. So now think if you're actually 3D printing with this. Those of you who have ever seen a batch ticket from a ready-mix contractor, you'll see the mix design they provide you is never exactly what you asked for, right? There's always some variance. So if your mixes are sensitive to 3D printing, you'll only benefit. If the amount of aggregates vary even a little bit, you're getting higher yield strength. But during vibration, they're roughly still the same. So vibration can still help print real concrete instead of lab-crete. Okay, similar trends, but at different volume of paste. So up to 70%, you'll see the more sand you have, the more yield stress you have. Beyond volume of paste, 70%, the paste rheology dominates more than the aggregate rheology. The y-axis is not the same in all of these plots. But yield stress, when aggregate is dominating the rheology, more sand you have, greater your yield stress. So sand to chip, the proportion plays a role in what your yield stress is. So next I looked at what happens if you change the aggregate. On your left you have, I changed the fineness modulus of the sand. The black line, the fineness modulus is 2.88, while keeping the coarse aggregate the same. On the right, I changed the coarse aggregate while keeping sand the same. So I had a gap graded limestone, so when recombining my aggregates, I just didn't add one of these sizes. And a river gravel. So if my coarse aggregate is circular, where there is not as much physical interlock, how does that change things? So first on the left, you'll see fineness modulus does play a role. Especially here, you'll see that there's a marked increase in the yield stress when it is not being vibrated. But during vibration, they're all roughly the same. So now you can independently control. So far, everything I spoke about, if any change that I made affected both yield stress with and without vibration. But now we are seeing something which can control only one of these two. And that will be crucial for 3D printing. And on the right, different kinds of coarse aggregate, you'll see they also impact your yield stresses, but not so much during vibration. So we now have found something which can only affect one of these two, but not both. Next, what if I change the paste while keeping the aggregate the same, right? So I added silica fume and fly ash. Silica fume makes the paste much more viscous, so it's harder for the aggregates to move apart from each other when they are being vibrated. So you'll see the yield stress drop is not as much, whereas at 7.5% silica fume replacement, at 2.5, huge increase when not being vibrated, pretty much the same when it is being vibrated. Fly ash reduces the yield stress. So depending on what you're putting into your paste, it can control your rheology. right? So now bringing all of this together in a ternary plot, my volume of paste varied from 40 to 100%, sand and chip varied from 0 to 60%. I used a special cubic canonical model to model the space. And this is what it looks like, right? Red is a lower number, darker the green is a higher number basically. So when you don't have a lot of aggregates, your yield stress is really low. And then you also see this minima that I was speaking about, right? Based on what your packing is, it can change. You'll see the more sand you have, higher your yield stress will. Now, yield stress during vibration, however, similar trends, but you'll see the more limestone chip you have, lower is your yield stress, right? And that is what you would want if you are 3D printing by vibrating your nozzle. Next, I used a central composite design method called Box-Wilson. It's an experimental design methodology where you can model an experimental space with a lot of variables very easily. In this method, based on the number of inputs, which is n here, and I had 3 inputs, volume of paste, volume of sand, and water to cement ratio. The number of factorial points will be 2 to the power n, 8 in my case, right? These blue circles. Axial points, the number of axial points is given by 2 times n, 6 in this case, and they're at a distance of alpha from the center. This whole model works on the central point. You repeat the central point multiple times to get what the variability of your measurements are, and then model the whole experimental space as a distance from your center. The model assumes the variability will remain the same, and variability changes linearly with the distance from the center. So these were my input variables: volume of paste from 30 to 50%, volume of sand 20 to 40%, and water to cement ratio of 0.6 to 0.44. So ICAR rheometer has a limitation. It can only measure rheology effectively when the slump is greater than 3 inches. So I had to kind of figure out what my extreme conditions will have to be so that I can still get reliable information from the rheometer. So I knew in these ranges I could always get values. So I made sure my axial points were basically these numbers. So I had to do some back calculation to figure out what my factorial points will be. It ended up being these. Volume of paste 30 to 50%, but my actual coded levels were 34% to 46%, and so on. So these are all the mixes that I had to do. 18 mixes, and then I can get to model the whole experimental space. So 8 factorial mixes, 6 axial, and I repeated the central mix 4 times to get a sense of what the variability is. Go through all these mixes and collect your all the results that you can. So I'm just showing some of my inputs here. So yield stress with vibration, without vibration. I also collected information about viscosity, what the density of the mix was, what the slump of the mix was, etc. But I'm only going to show yield stress today. So once you have all your model inputs, you fit 4 curves into your results. So the response, so yield stress, for example, you fit it with constant term and a linear sum of your input variables. That's equation number 1. Equation 2, constant, linear term and square term. 3, you add an interaction term as well. And 4, you add a square term as well. So you get 4 equations for each response. And then you figure out which one has the highest adjusted R-square value. Whichever has the highest adjusted R-square, that becomes your equation for that response. Right? So for yield stress, it turns out I needed a constant term, linear term, and a square term, whereas for the yield stress during vibration and viscosity with and without vibration, it was a full quadratic equation. This is what the equations looked like, and what the adjusted R-square was. It was somewhere in the low 90s. And I used a statistical software called Minitab to crunch the numbers, and the software gives out these plots. So on the left is a Pareto chart, and this one is for yield stress. What those bars represent are basically a p-value test is run. P-value test basically tells you how much of an influence your input parameter it calculates the probability of your input parameter not having an effect on your output parameter. So the lower your p-value, it means your input parameter has an effect on your output, right? So this is standardized here. So the larger the bar here, it just means that input parameter does affect your output. So for C here stands for water cement ratio. Water cement ratio has the greatest effect on your yield stress based off this model. And on the right, I have a normal plot. It tells you if this effect is positive or negative. So C has a negative correlation. So you reduce water cement ratio, your yield stress goes up. But that does have the highest statistical influence on your rheological property. The second highest was A, that is volume of paste. So volume of paste has an indirect relationship with your yield stress, right? You reduce volume of paste, meaning you increase your volume of aggregates, your yield stress goes up. Similarly, for yield stress during vibration, there were some parameters which did not influence the output, but there were 3 or 4 which did. A being volume of paste, a negative relationship with the yield stress during vibration, and so on. So I've summarized all of those in this table here. So statistical significance based off ranking. So if you want to change your yield stress, the best way to do it would be to reduce your water to cement ratio. The second best option would be to reduce your volume of paste, and so on. So we get this whole relationship. So now if you can have a trial mix of your 3D printer, see what is happening. Based on what your mix looks like, you now have a cheat sheet to change. What should be the first thing to change? What should be the next thing? But say you can't change one of these. What is the next best alternative? So this gives you a tool to do some more iterations. Now, because we have those equations, you can also plot and kind of zone in on what your first trial mix should be. I've picked some random hypothetical targets here of viscosity during vibration should be between 15 and 30 pascal second, yield stress during vibration, yield stress at 0.38 water cement ratio, right? Because we have those equations, and within that experimental space, all these responses have been modeled. You can zone in on, okay, maybe we should start here. This should be the properties for my first trial mix. You'll need to adjust it a little bit, but you're not flying blind. So I modified an existing mortar and cement paste printer by having pneumatic turbine vibrators, and I had about 2-inch wide nozzle. Based on calculations, I could have printed much wider and higher layers, but the limitations of the 3D printer forced me to choose 2 inches. So the way this works is I have really stiff concrete. This is top view, and when I vibrate it, it starts moving, flowing down. At the bottom, this is what it looks like. As soon as I start vibration, concrete flows out of the nozzle. There were no chemical admixtures in any of my mixes. This is pure concrete, cement, water, sand, and coarse aggregate only. So it's not as sensitive to outside parameters. Concrete can take a lot of beating, right? Ignore the first 2 inches. I did not have the capability to rotate my nozzle, so I had to start and stop. I was not stopping to let the layer below to gain some strength. I was continuously printing. But because I was stopping, there was a dead zone. So if you ignore the first 2 inches, you'll see it's a nice clean print. And this had water cement ratio 0.34, 44% paste, 56% aggregate. So, the interest of time, I'm gonna show all of it at the same time. So I started printing on one end, noticed some defects. From my CCD model, I knew which one to tweak first. I did that, got some really bad results, so I could fine tune based on what the output looked like. I also had a subjective ranking scale. That's the red one was really bad, green is really good, or somewhere in between. Now, rheology takes a lot, especially for concrete, you need a lot of material and a lot of time to actually come up with these numbers. So is there a way to indirectly measure rheology was the next thing I looked at. Slump test is pretty easy and straightforward, and especially in the field to do. And I modified flow table. It's not meant for stuff with coarse aggregate, but I still considered it. I measured these two values for all of my mixes, right? And looking at my subjective ranking scale and what all the mixes which I was able to successfully 3D print, they all had two things in common. They lied somewhere in between 1 and 1.5 inches of slump and 3 and 3.5 inches of spread. Okay? So now I did some back calculations or regression analysis to see what is the yield stress and the viscosity of these mixes if they were to have slump between 1 and 1.5 inches. Right? This will now give me, based on where the lines intersect y-axis, some targeted rheology. So spread and with yield stress and viscosity, it's saying the rheology of, for my system, the rheology had to be between these numbers for me to be able to print successfully. So going back to the CCD model and putting the numbers that I now know as my boundary conditions, I have these small white zones where I should have successful 3D prints. And the stars are where I actually, my actual successful prints were. So that's quite good correlation. There is a model, there is some variability, but I was able to accurately predict what rheology I need and how to achieve that. So vibration has an immediate and reversible effect on concrete's rheology. Aggregate content is important. CCD can be used to model experimental space, and to predict the performance of 3D printable concrete, we could potentially use established tests like slump and slump flow, and if you have a established regression analysis, you could back calculate what your rheology should be. And I didn't talk about this in my presentation today, but how much vibration goes into your concrete also plays a role on how low your yield stress can go during vibration. So, you can predict rheology of concrete, as the title of the session says. Thank you. I'm happy to take any questions.
Great job. I have a few questions.
Sure.
First, the vibration frequency. Mm-hmm. So what's the frequency you test?
Give me 1 second. I don't remember off the top of my head, but 1 second.
Okay. So my question to you is, there should be an optimized range of frequency, right?
Yeah.
If it's below, it doesn't work. If it's over, then you overkill.
Yeah.
True. So my question to you is, so your testing is at one frequency, or you test a range of frequencies to prove your, this conclusion?
It's more than frequency. I found that it was the energy of vibration which matters. So amplitude times frequency square. That is what matters. So how much energy you're giving into the system is what dictates the change in rheology. So it's a combination of both. So it's really hard to come by vibrators where you can independently control one or the other. So it usually changes both at the same time. So I looked at 2 or 3 different frequencies, and the trends remain the same, but how much of the change in yield stress during vibration expressed as a percentage, that changes.
So you list over here.
So this is of the vibration table itself.
Yeah, so 60 hertz,
Yeah.
So also amplitudes, just 0.001.
Mm-hmm.
So certainly, those will affect your
For sure,
total, vibration energy, right? Okay. Mm-hmm. Another question is, so I see some people, they do the vibration, on the hose, okay, because the material is, low slump, zero slump.
Yeah.
And you are testing the vibration, at the printing head. Mm-hmm. So do they work the same way? Which one is better? Or any comments on that?
So when you start vibrating, there is some dilation occurring. So cement paste tends to move towards the outside and helps concrete move more easily, right? So that's what I said. Like on this slide, I mentioned I'm putting low slump concrete at the top and doing whatever necessary to get it to the nozzle, right? You can, that's an engineering problem there more than a concrete problem. You can solve that in multiple different ways. You can vibrate it. That's what I ended up doing. But you could have a pressure head. I did not have a 3D printer which could easily do it, so I ended up vibrating to get it there and manually filling the hopper as concrete got consumed. But if you're scaling this up, that shouldn't be a harder thing, right? You could pump concrete there, wait some time for it to lose its lump, or use chemical admixtures to get it to become stiffer.
Yeah. So your conclusion, the whole rheometer, just the, testing, would that, affect if you have the vibrator on the hose? That's my question.
It shouldn't. It shouldn't.
Yeah. Okay. Yeah. Thank you.
I'm happy to talk to you after this.
Yeah.
Yeah.
One more question.
Sure.
Thanks. Very nice presentation. Try to be quick with the question. So, have you tried to study also interlayer bonding with regard to this procedure? Because it seems to me that after you vibrate the material, the yield stress goes back to be high very fast.
Yeah.
So maybe you tend to have less flowability, and maybe interlayer bond is not developing good.
Because I'm vibrating, more cement paste tends to flock to the outside of the nozzle, so there is actually really good connection. I didn't show it here. There is really good interlayer bond, 1. 2, because of the high yield stresses, I calculated for my density and for the yield stress I was getting, each layer could be 8 inches tall without it collapsing. And I don't have to wait between layers, so these will just help reduce the number of layers, and there is no cold joints formed as well. So any issues if we do have with interlayer bonding, there are so compare it with how we are 3D printing now in general, right? We are in millimeter scales. I'm saying with this, something like this, we could have concrete so stiff that you could have 8 inches.
Okay, no, so just you check that there are no voids, no air.
Yeah, there are no, I have photos of the cross sections.
Thanks.